So overall, Lab 4 results were pretty good. In fact, the performance of the controllers is better than with the 8-bit microcontrollers. We're not entirely sure why. Although the threader has a lower latency and therefore more cycles go into computation and probably the floating point is faster. But the performance of the control systems is quite a lot better on average. Or it could be just the students are better. Secondly, we have, towards the end of the semester, there will be a evaluation for the course. And with a bazillion online evaluations, find that the participation goes down. And we really need feedback on courses to be able to tune them and figure out what to do. So I've been toying with the idea of making it for credit. Do people have, what do people think about requiring a course evaluation? Does this bother you? Do you think it's a good idea? So it's okay? And did you feel put upon by having it required? It's just a free point, right? Free point. So you're pretty much okay with it then. I was trying to figure out whether it would cause a positive or negative bias in the results. And I don't know. Because there's so many competing factors that it's impossible to tell. Okay. So I'm going to finish up talking a little bit more about physical synthesis that I started last time, physical music synthesis. Then I want to talk a little bit about PIC as a standalone system, which somebody asked about weeks ago, and I lost it someplace in my head. And I've started looking up HID stuff. There is a approved microchip HID library for the PIC32. That's the good news. The bad news is it's not targeted at our board. And so you have to modify the I/O slightly on the low-level I/O to make it run. That's a pretty glib thing to say. I don't know how hard that is. So, any questions at this point about final projects? Remember, you are required to be in your lab section every week. And the TAs probably, by today, will have sent out a description of what they expect, but every TA expects a weekly update. And the performance piece of the lab, 20% of the final project, is routine advancement on the project. Excuse me. The performance grade will be based upon the material you turn in for the progress reports. So you come to lab. We chat. The first week is liable to be a lot of head scratching and planning and fiddling with hardware, but also it's a chance for me to talk to you and to find out what's going on and make sure that we're all on the same page. Help you find parts in the lab, whatever you need to do. I will be there minimally Wednesday afternoon, Thursday afternoon, Friday afternoon. Anybody going to come in tomorrow morning to work? Nah. Yeah? Possibly. Okay. Well, I have a meeting at 9. But just feel free to interrupt me at any time, and I'll open up the lab for you. And then we can, and I'll be there after that. Final project questions. Okay. So last time, talked a little bit about how to make a physical model, a computationally efficient physical model of a string or other wave resonator on the microcontroller. Let's see, fat chalk or thin chalk? Which resolution do you like better? Fat? Okay. And the basic observation from Karplus and Strong in the 80s is that the solution of a wave equation can be represented as a traveling wave, and a traveling wave can be represented as shifting a waveform through a circular buffer, so that in the end you're going to have a buffer. Using the fat chalk makes me slow down slightly writing, which is probably a good thing. You're going to have a buffer whose output is fed back through a filter, then a tuner, and optionally some other modules, but minimally a filter and a tuner. The length of the buffer will correspond to the length of the string, and therefore the fundamental frequency will be set by the length of the buffer plus the fractional tuner. So the length of the buffer is always an integer, and the tuner then will be a length of buffer between 0 and 1. And the way I implemented the tuner was as an all-pass filter. So the tuner is the output of the tuner at time n is equal to some constant times the input at time n minus the output at time n minus 1, so it's an infinite impulse response filter, plus x n minus 1. So this kind of interpolates between x n minus 1 and x. And if you need a delta 0.1 less than or equal to delta less than or equal to 1, then the parameter is equal to 1 minus delta over 1 plus delta. So this allows you then to have a non-integral length circular buffer, which you need to get within. How accurately do you think you can detect a tone? How accurate does tuning have to be, would you guess? Or if some of you are musicians, you might know. Well, yes?
1 hertz?
Well, it turns out it's relative to the frequency, because your sense of pitch is logarithmic. So if it's 1 hertz at 100 hertz, it might have to be 10 hertz at a kilohertz. But the best I have heard of are people with perfect pitch who could tune to 0.1%. So that's way better than I can do. I probably can't do 1%. But someplace less than 1% and bigger than a 0.1% is probably a reasonable range. So for a buffer tune to middle C, which at 8 kilohertz corresponds to about 30 buffer steps, just tuning to the nearest buffer step is going to give you 3% accuracy, and that's going to sound horrible. So you have to have this fractional tuner here to get the fractional step. And the original karplus filter was to just average together a couple of buffer outputs and feed it back. So it's just a simple averaging, a running filter, really, a two-entry running filter. And again, I don't have any code for PIC32 yet, but hopefully somebody will generate this for us for a final project. But I do have some code left over from AVR. And to find that, you have to go, this is the usual home page. There's an obscure link down here that says old AVR homepage. So we go there, it looks the same, but different. And under DSP for AVR, a bunch of stuff. And there's a C code. The C code is this horrible thing is a assembler macro which does multfix. I haven't done that on PIC32 yet because I haven't learned the assembler well enough yet. But the heart of the matter is down here in the timer 1 interrupt service routine, where you take a sample out of this the string. String here means like guitar string, not character string. Take the oldest sample out, shift it around, add an offset, and output it to the pulse width modulator, just like you did in PIC32. Then we take to compute the low pass filter, we take the oldest two samples, add them together, divide by 2, takes the average of the two, so it's an averaging low pass filter. We multiply by some damping coefficient so that the loop gain is less than 1, because if it's greater than 1, it's not a string anymore, it's an oscillator. Then tune the output of the low pass filter. So it's low pass out plus last tune out plus last tune in. So that's just the recursive formula I showed you on the board a minute ago. Update the state variables, update the string pointers. Done. So it's very little code to actually implement. Oh yes, if a pluck occurred, if the human asked to pluck a string, then the string is loaded with noise, pre-computed noise, which could be literally white noise, or could be some more coherent shape, depending on the effects you want. Any questions on this? It's really straightforward to do. Straightforward C code. Makes a good sound. And on the AVR, which was running at only 16 megahertz and 8 bits, you could expect to do between 6 and 12 strings per update at 8 kilohertz. So you can do probably at least 5 times that many on the PIC32. Any questions on synthesis? Anybody intend to do any music synthesis? Want to talk about it? Yeah. What are you thinking about doing? Remind me. Piano. Piano. Oh well, you can't think of a harder thing to synthesize than a piano. So piano dynamics are nonlinear. And the reason they're not, there's a couple of reasons they're nonlinear. One is, particularly for the lower tones, the strings are so thick that they no longer act like a second order wave medium. They start acting like some sort of combination of a nonlinear second order wave and a fourth order stiff rod vibration. So you get this weird effect from that. Another reason is that strings tend to be hit in threes with interaction between them through a sounding board. So these strings are hit in threes, and you have a hammer which comes down and hits the string, gets thrown off the string by the bounce of the string, comes back down and hits again, and acts as a pointwise nonlinear boundary condition on the string at one of the highest energy points, which is where you're bouncing it. So you get these interesting nonlinear effects, which to make it sound right you have to include, particularly at lower frequencies. But that's typically, I have some information specifically on piano synthesis you may want to look at. Anybody else thinking about doing string synthesis? It works well. It's pretty easy. So one of the requested topics was to talk about using the PIC in standalone. And there is very little that you need to do to make one of these things run on a whiteboard or on a solder board or whatever you want. All you really need is a 3.3 volt power supply. So if we have a PIC32 here, the pin 1 is a reset line, and typically what you want to do is to pull this up to 3.3 volts through something like a 10K resistor or so. And then if you want to be able to manually reset it, you need to put a push button to VSS. This line also has to go out to the programmer. Pin 8 is VSS. Of course, we need VDD, and that's going to go to 3.3 volts, but also as close to the chip as possible. Preferably not more than a couple of tenths of an inch. You need to have a 0.1 microfarad disc ceramic to ground. It has to be disc ceramic because it has to be high bandwidth. And there's an AVDD that needs to also go to 3.3 with a disc ceramic to ground, 0.1 microfarad. There's this strange thing called VCAP, which requires a 10 microfarad polarized capacitor to pin 20. And I think that's for an internal voltage regulator. This should be a tantalum capacitor and not a electrolytic. Then the final two leads are PGO and PGC, pins 4 and 5, which go off to the programmer. So the programmer is going to jerk the reset line down and then manipulate these two port pins to program the CPU. But that's all it takes. Yes, they can. How are you going to get 3.3 volts? Well, I bought some low dropout regulators. I bought some MCP 1702 3302E regulators. 3.3 means 3.3 volts. 02 means I bought the cheap ones. 2%, and E means it's a temperature range. These babies will work hot. They can be too hot to touch, and they are fine. They start to fail at 125 C. So if they're working flat out at 500 milliamps or so, and you touch them, you can burn yourself. They're very easy to use. There are 3 leads: ground, V in, and V out. V in has to be 3.8 less than or equal to V in less than or equal to 14 volts. And V out will be 3.3 volts, and there has to be a 1 microfarad or so ceramic capacitor on the input and output. Dropout voltage is about half a volt, so you could certainly run these off of 3 AAA cells, or probably a lithium-ion battery, or in fact any of the wall warts that we have in the lab, the 9 or 12 volt wall warts. Any questions?
How much do these cost for like
Budget? Oh golly, I think these were around $1. It would be very interesting to see if the thing would just run on 2 AA's with no regulator. It should, if the impedance is low enough of the batteries. So I linked up a few resources here down in the link section, except apparently I haven't refreshed this lately. So I linked up some standalone information. So one is the data sheet for the LDO regulator. Another is from Tamid. So if we look at Tamid's development setup, that's it, folks. He even stripped down the circuit further. There's the 10 microfarad capacitor, and that isn't even a tantalum, it's an electrolytic, and it seems to work. And 1 bypass capacitor right here. The fact that it boots up is slightly amazing, but it works. This thing down here that you can barely see is a PIC32 programmer. It has 6 leads. For small currents, less than 30 mils, you can run the microcontroller directly off of the power supply in the PIC32. It's a bad idea because if you do that, as soon as you disconnect the programmer, of course your system doesn't work. Secondly, it's limited to a fairly low current, so you're probably going to want to use a regulator. When you plug in this device, as near as I can tell from the documentation, it auto-detects the power supply which is connected to the PIC32 and adjusts itself automatically. So it should just work using the 3.3 volt regulator. Questions? So now if we, I found this link to be pretty useful. The PIC kit and PIC32, because it had lots of nice pictures. In particular, it had a picture of running the PIC32 directly from the PIC kit, assuming low current, and then more generally, crash, bam, assuming a power supply. And this is just using an LM317, which you're not using. You're using a better regulator than that. And you notice that the output of the regulator goes to the voltage input or output of the PIC kit. So the power is now being supplied by here, but being detected by the PIC kit. And neither of these systems has a hookup for an external clock, for an external resonator. But you will find that if you want to If, for instance, you want to use a USB, if you want to use a USB connector, you will have to have an external crystal. The internal crystal is not accurate enough, and in fact the USB will not turn on unless you are using the external clock. That is to say, an external resonator at 12 megahertz. Still a pretty simple circuit. Whoever built this also put quite a lot more bypassing on. That's the tantalum, big tantalum capacitor. These are small little disc ceramics probably. The programmer connection is obvious over there. So, and I believe that's the regulator. So that's kind of the minimum circuit you need if you're going to do USB stuff. Any questions? Did I see a hand go up? Okay. So it's easy to get running on a whiteboard. Yes?
So for doing the standalone, do we have to make the kits?
Yes. Yeah, I have 20 or 25 of these things in the lab. Can't take them out of the lab because I have about one per station. So if you're going to make a standalone system and you want to work on it at home, you better buy one of these guys. The oscillator is a crystal. It probably would be between 50 cents and $1. I have 8s and 16s in the lab, 8 and 16 megahertz. But I think for USB you have to have precision 12.00. The internal oscillator is guaranteed to be within a percent. A crystal external to the CPU will be accurate within 50 parts per million. So that's 0.005%. It's much, much closer tolerance frequency source, which is what you want to use. Now, putting a crystal on a whiteboard is tricky because the total capacitance of the whiteboard is close to the maximum limit at which the crystal will no longer oscillate. So the fact that this works on a whiteboard is slightly surprising. You may not actually even have to connect any capacitors to the crystal, even though that's the standard way of hooking them up, because the board capacitance will take the place of the capacitances to ground. Normally when you hook up a, wow, it's a spring-loaded PDF. Normally when you hook up a crystal, you symmetrically hook up two capacitors to ground, and the other two go into OS1 and OS2 inputs of the CPU, and I believe that's 9 and 10, pins 9 and 10. But the board capacitance is high enough, you may be able to just leave those off. That you have to experiment with. You can make a low-value capacitor very easily by taking two pieces of wire and twisting them together, and then plug them into the whiteboard, and if they're too much capacitance, you untwist them a little bit. That's probably more than enough capacitance to run the crystal. It only takes a few picofarads. If you merely touch something, what is your body capacitance? Brian? 40 picofarads. He measured it in lab last year. And it's an interesting measurement. It's a very interesting measurement. And the way he did it was to put a 1 meg resistor. It was a 1 meg resistor to the signal generator. Hold on to the end of the 1 meg resistor. And then hook a clip lead to the resistor and just hang in space. And you are a capacitance to ground. About 50 picofarads. Some of the bigger guys might be 100. Depends on surface area. So who's going to build one of these things? Oh, we also have some boards. We have some boards that are pre-punched for this. It'll require some surface mount soldering. Or you can put them onto a whiteboard. Anybody going to build their own boards? Because you want to do USB. Yeah. One of the MN students last semester built used the microchip libraries to build a USB host. That is to say, you could plug a keyboard into the PIC32 or a mouse, and the PIC32 then would get the keystrokes or the mouse motion. But she did not do any device programming, only host programming. So you hook a USB type A connector and plug in your mouse to it. That's interesting. That's working. So there's why not just use an FTDI chip? For serial communication, that is certainly a reasonable thing to do. But if you want to treat the PIC32 as a human interface device, input to the PC, then that won't work. Although FTDI does make an HID chip also that will treat serial input as a HID device. But the PIC32 will run a USB HID device natively. The USB transceiver is built into the so if we go down here and look at I found 2 USB descriptions for PIC32. One is called MStack, which seems to be some sort of open source thing. And the other is USB class on an embedded device from Microchip, which probably has better documentation, assuming it's correct. So virtually all I know about this is what's in application note 1163. No student has tried this. Nor have I. That means it makes a good final project. Right? So it should be, it should work. The various forums that are available on Microchip suggest that it's not too hard to get working. This is really all, I mean, I can go through this some more, and I might be able to by the end of the week, but then MStack, USB stack 4, blah. All right, device, HID, vendor-defined no-class devices. Mass storage class devices. Oh, so you turn the PIC32 into a flash drive. One thing to be very interesting to do would be to with the USB host, with running a USB host on the PIC32 to try and read a flash drive on the PIC32, because then you'd have effectively infinite memory. The host code, by the way, takes up about 50% of flash on this chip. So what do you think? Let me show you the projects from last year, the MEng projects, since I try and shamelessly use MEng students to develop code for courses. Alex Whiteway did a really nice job on getting Ethernet running and USB running. So the chip we have, the MX250, has a USB MAC and fizz layer built on it. All you have to do is put a connector on, and it works. The Ethernet requires an external MAC and fizz chip. So he got that running with a microchip, ENJ, whatever it is, Ethernet interface, and could stream music using connection, stateless connection, not using TCP but UDP to the PIC32. And these, if we follow the link to the PIC32 development, we go to my standard small web page for MEng projects, but the full report's here, and the code is all here. So there's quite a lot of descriptive material on how to get Ethernet running and how to get USB running. Then another project, Shinran, close, Shran, you, worked on getting a USB host running. She got completely decoded keyboard and mouse. So again, her full report is here, and might be of some use, I hope. So what I'm trying to do now is I'm trying to get decent speech compression running on the PIC32 by means of, so I wrote code that would do a 25 channel spectral decomposition. So it puts 25 bandpass filters in the range of 100 hertz to 2 kilohertz. Looks at the energy in each band, takes the average energy in the band, passes it off to a synthesizer, which then uses that to control the amplitude of a single sine wave. So you're taking all the energy in a given band and converting it to one sine wave energy, and then playing that back. And amazingly, it sounds like speech. You've taken whatever mess you're producing out of your mouth and replacing it with 25 individual sine waves of logarithmically related frequencies. And when you play it back, you get something like a 10-to-1 compression in terms of number of bytes to produce the speech. And it sounds kind of slightly bird-songy, because that's how birds sing using sine wave oscillators. And but it's understandable. So as soon as I can get that going, I'll whip up a web page on it. I have the analyzer side running on the PIC. I've got the synthesizer running on the PIC, but with dud data, with no real speech data yet. It will run in real time. So you can speak into this thing and it will produce synthesized voice in real time. But it'll do arbitrary pitch shifting, which is kind of cool. And you can do very odd special effects with it, like pitch inversion. So should be interesting to get running. Does anybody think about doing pitch shifting, voice pitch shifting? I thought there was I want to talk to you if you're interested in that. So I think I know how to do it. Okay. There was one more. I could try and do a little more on USB, but since I haven't done it and no student has done it, you're just waving in the breeze. But I have great faith that you can make it work. I think that the libraries are there. Bluetooth I could talk a little more about. And that I think was about all that was requested. So what's the feeling, folks? More lectures? Go to the lab. I know what the answer to this one is. What do you want to hear about? You want to hear about something else? Do you want to just start working in the lab? If you're working in the lab, remember now, as soon as we stop lectures, and you have nothing else assigned, after this week, I expect 12 hours of work in the lab a week. Well, 12 hours of programming a week. It could be in the lab, it could be outside the lab, but I expect 12 hours a week because you have nothing else assigned. Say again, flash ADC? There is no flash ADC. It is a 1 megahertz bandwidth successive approximation ADC. So if you want to do a flash conversion, you'll have to get a flash, external flash ADC. How fast do you want to go? It's about a megahertz. A flash ADC, by the way, is a device that does the conversion by the simple expedient. If it's an 8-bit converter, it has 256 comparators on it, and it compares the voltage to 256 different values, finds the one that's closest, and outputs that. And you can get those things running up to around a gigahertz. But remember, if you're going to go that fast, circuits no longer look like lumped devices. They look like waveguides. And now you have to do, instead of laying out wires, you have to do strip line to get the signals through the system. If anybody wants to talk to me about strip line, we can do that offline. That's non-trivial exercise. Uh-huh.
Would the easiest way to do that is to store all the sounds would be like the
So you're saying how to store sounds or how to play them back?
And also just the interaction between, because we're doing two different things between the left and right, so I'm wondering if that's more involved.
So you're going to have to, do you have a fixed set of sounds you're going to play, or do you have, are they arbitrary sounds?
We'll probably have to fix.
If it's a fixed set, you can put them in flash memory. If you run out of flash, you have 128K of flash. If you run out of flash, then you're going to have to put them in external flash RAM. You can buy a 8-pin PDIP flash RAM from either Atmel or Microchip that'll hold 100 megabytes. Put all the data on it you want. You have to figure out how to get it there. But once it's there, you can use it over and over again. So the playback is is a separate problem. You might find that you have to use an external DAC like you did in Lab 2, stereo DAC, and you could DMA it. Tamid figured out how to DMA to the DAC. It's on his blog. So what's the feeling, folks? Well, we will have lab on we'll have lecture on Wednesday because there's no conclusion. See you back here Wednesday.